Okay, let's just dive right into this. Welcome to today's Explainer, where we're going to unravel literally one of the greatest cosmic mysteries in modern astronomy, Type A supernova. Now, you probably know these aren't your run-of-the-mill exploding stars. They are the fundamental measuring sticks of the cosmos. I mean, they're incredibly bright, sometimes outshining entire galaxies, and they are the exact tools astronomers use to figure out that our universe's expansion is actually accelerating. But here's the catch. Despite relying on them to map the whole universe, we actually still aren't entirely sure exactly how they ignite. It's a literal stellar cold case, and today we're going to look at the evidence. So here's our roadmap for today. First, measuring the accelerating universe. Then, anatomy of a stellar bomb. Third, the progenitor's suspects. After that, the double detonation curveball. And finally, the future of the hunt. All right, part one, measuring the accelerating universe. Before we figure out how these stars explode, we kind of need to understand why they matter so much to us down here on Earth. And it starts with a massive question. How do you measure the edge of the universe? You obviously can't string a tape measure across billions of light years. And in the vastness of space, it's remarkably difficult to tell if a light source is just, somewhat dim and close by, or incredibly bright but impossibly far away. To solve this, astronomers desperately needed a cosmic measuring stick. And the solution is what we call a standardizable candle. Basically, it's an astrophysical object with a known intrinsic brightness. Think of it exactly like a light bulb. If you know for a fact you're looking at a 100-watt bulb and it appears really faint to you, you can use the physics of light to calculate exactly how far away it must be. Well, Type 1a supernova are our cosmic 100-watt bulbs. When they reach peak brightness, they emit a luminosity roughly 4 billion times that of our sun, and because the physics that triggers them is so incredibly specific, astronomers can mathematically correct for minor differences in their light curves to figure out their precise intrinsic brightness. As researchers have noted, thermonuclear supernovae have been identified as standardizable candles, making them invaluable tools for cosmology and leading to the discovery of an accelerating universe. By measuring these precise distances across the deep cosmos, astronomers back in the late 90s realized something mind-blowing. The furthest supernovae were dimmer, and therefore farther away, than they should be if the universe's expansion was slowing down. That realization? That led to the Nobel Prize-winning discovery of dark energy, that mysterious force causing the expansion of the universe to accelerate. Okay, let's move to part two, anatomy of a stellar bomb. So we know they're useful, but what actually causes this incredibly precise explosion? Well, first, we have to separate Type I from the rest of the pack. You've probably heard of massive stars collapsing at the end of their lives, right? Those are core collapse supernovae. They happen when giant stars, heavier than 8 solar masses, run out of fuel and just cave in on themselves. But Type I supernovae are fundamentally different. They are thermonuclear explosions. They don't happen to massive stars. They happen to medium mass stars, much like our own sun. When a star like ours dies, it sheds its outer layers and leaves behind this hot, incredibly dense core of carbon and oxygen called a white dwarf. And it's this dead remnant that eventually becomes our bomb. But a white dwarf just sitting there alone in space isn't going to explode. It's actually stabilized by something super fascinating, electron degeneracy pressure. Because of a quantum mechanics rule called the Pauli exclusion principle, which basically says electrons absolutely refuse to be crammed into the exact same space, kind of like people in a hacked elevator, they move at incredible speeds, pushing back against the crushing weight of gravity. But there is a physical threshold here. It's called the Chandrasekhar mass limit. If a white dwarf's mass approaches roughly 1.4 times the mass of our sun, gravity starts winning. So let's walk through the actual timeline of the explosion. Step 1. The white dwarf gains mass from a companion star. Step 2. It approaches that 1.4 solar mass Chandrasekhar limit. The temperature and density just completely spike. Step 3. This extreme environment ignites carbon fusion right in the core. But here's the thing. Because the star is made of degenerate matter, it can't expand and cool down to regulate the reaction like a normal star would. Which leads directly to step 4, a runaway thermonuclear explosion that completely obliterates the star in seconds. And step 5, and this is absolutely crucial, the explosion forges huge amounts of a radioactive isotope called nickel-56. So that intense brightness we see from billions of light years away, that's actually not the initial fireball. It's literally the glow of radioactive nickel-56 decaying into cobalt-56 over the following weeks. Moving on to part 3, the progenitor suspects. So, we know the weapon, a carbon-oxygen white dwarf, and we know the trigger mechanism, approaching that mass limit. But who's the accomplice, right? Where does that extra mass actually come from? This is the absolute core of our cold case. Astronomers have narrowed it down to two main progenitor suspects, the single degenerate model and the double degenerate model. And just as a quick reminder, degenerate here just refers to the white dwarf. Let's compare the suspects side by side. In the single degenerate model, our white dwarf is paired with a normal, non-degenerate star, like a main sequence star or a red giant. It steals gas from its companion, siphoning it off until it explodes. Astronomers look for key clues for this, like blue-shifted sodium lines in the spectra, which basically points to gas blowing off the system right before it blows up. Now, in the double degenerate model, the companion is actually another white dwarf. The two dead stars orbit each other, losing energy via gravitational waves, spiraling inward until they violently merge. The key clue here? Absolute destruction. A merger leaves no surviving companion behind. So we have to weigh the pros and cons of these suspects. The single degenerate model naturally explains why all these supernovae look so identical. They all explode right at that exact 1.4 Chandrasekhar mass limit. But the physics is pretty messy. The accretion rate has to be absolutely perfect, about 1/10 millionth of a solar mass per year. If it's too slow, the gas just burns off in small nova flashes. Too fast, and the white dwarf gets smothered in a common envelope. Now, the double degenerate model used to be the underdog, but it's gaining major traction lately. Why? Because when we look really closely at the remnants of Type Ia supernovae, we almost never find a surviving companion star. A merger neatly explains that absence. Section 4, the double detonation curveball. Just when astronomers thought they were closing in on an answer, the universe threw a massive curveball that challenged everything we thought we knew about that strict 1.4 mass limit. 0.76 solar masses. Take a look at that number. In May 2018, an optical survey called the Zwicky Transient Facility detected an event named ZTF-18AQSU. When researchers analyzed the data, they realized the white dwarf that exploded was incredibly light, only 0.76 times the mass of our sun. That is way, way below the Chandrasekhar limit. So how on earth did it explode? Well, the answer is a double detonation. Let's look at how this builds a completely different kind of bomb. In this scenario, the white dwarf isn't stealing hydrogen, it's siphoning a thick shell of helium from a companion. When that helium shell reaches about 0.15 solar masses, the pressure and heat at the base of the shell cause the helium to detonate first. This surface explosion sends a massive, crushing shockwave inward. The shockwave compresses the lightweight carbon-oxygen core so intensely that it forces a second, central detonation. Boom! You get a supernova well below the mass limit. And because of the burnt helium and the weird dynamics, it produces an unusually red, somewhat dimmer explosion, with these really strange spectral cutoffs from metals like iron and titanium. All right, our final section, the future of the hunt. This double detonation discovery totally proves that the Type Ia family is way more diverse than we ever imagined. So how do we solve the case and use these varied standardizable candles to accurately map our universe? Well, NASA is making a massive investment in this exact puzzle. As the quote here says, the Nancy Grace Roman Space Telescope will conduct a generation-defining experiment in time-domain astronomy to better constrain the nature of dark energy. This upcoming flagship mission is specifically designed to hunt down Type Ia supernovae across the cosmos. Here's the timeline for the future of cosmology. First, we're currently using ground-based surveys like the Zwicky Transient Facility to catch these stellar bombs just days or even hours after ignition. That lets us see early flashes that hint at companion stars. Second, the Roman Space Telescope is slated to launch by May 2027. And third, Roman will execute the High-Latitude Time Domain Survey. By building a massive, completely unprecedented dataset of Type A supernova, astronomers are going to be able to filter out the weird curveballs and use the pure standardizable candles to precisely trace the history of dark energy. Which brings us to our final slide, and a really massive question to ponder. As we finally decode exactly how these white dwarfs turn into stellar bombs, and as we use them to measure the accelerating expansion of the cosmos with unprecedented precision, what will these standardizable candles ultimately reveal about the final fate of our universe? I mean, will the expansion tear everything apart, or is there another twist waiting in the dark? It is an absolutely incredible time for astronomy, and I really hope this explainer helped you grasp the immense power and mystery of Type I supernova. Keep looking up and keep asking questions.